This video is about how to find the dew point and the bubble point of a multi-component mixture. And this may be a bit of a new concept for you, and to be quite honest, it's kind of a little bit counterintuitive at first. And that is because for pure components, you've known for a while that vaporization and condensation occur at the same temperature. So say that you had water at 1 atmosphere and it was in the liquid phase at 80 degrees C. You know that because the boiling point is 100 degrees C, if you were to heat that water from 80 C to 110 degrees C, for instance, the boiling would occur at 100 degrees. Now, if you took that water and then cooled it back down from 110 back down to 80, the condensation would also occur at 100 degrees. Yet for mixtures, the vaporization and condensation does not occur at the same temperature. So we'll start off with some definitions. The bubble point is the temperature or the pressure that vaporization of a liquid mixture begins. In other words, it is the temperature at which the first bubble of a liquid mixture forms. So I'm careful to say here temperature or pressure. Remember, there's two ways that you can vaporize something. If you have a liquid mixture, you could either increase the temperature or decrease the pressure. Both of those are going to have the same effect. The dew point, on the other hand, is the temperature that condensation of a vapor mixture begins. You can also think of it as the point at which the first droplet of liquid forms. And here, once again, you can do this in two different ways. You can either decrease the temperature or you could increase the pressure to reach the bubble point. So whenever we say dew point or bubble point, we have to also clarify whether or not we're talking about temperature or pressure. So it'd be bubble point temperature or dew point temperature, or bubble point pressure or dew point pressure. And as you would expect, the bubble point temperature is always, greater than or less than. If I've thought about this correctly, I think I have. The bubble point temperature is going to be less than the dew point temperature. The bubble point pressure is going to be greater than the dew point pressure. So when I'm talking about solving for the bubble point and the dew point, this is again using Raoult's law. And I'm going to use Raoult's law in a way that combines the two equations. So let's start off by finding the bubble point. So bubble point constraint. So when calculating the bubble point, I'm going to set the constraint that the vapor phase mole fractions have to add up to 1. Now, of course, this is true in any case, but for the bubble point especially, because I'm using the vapor phase as the constraint, this is what I'm going to use as my basis of calculation. So I'm going to write my two Raoult's laws. For components A and B, that would be YA times P. So here are my two Raoult's laws. And I'm going to combine them by adding them together and then using the fact that I know that YA plus YB must equal 1 as being my constraint. So if I add these two, I'm going to have, the P will factor out, right? So P factors out YA plus YB. This is where it's useful to say this is equal to 1, is equal to XA PA star of T plus XB PB star of T. And nothing factors out on the right-hand side because these vapor pressures are for different components and they are therefore different. However, the temperature is the same. Therefore, if I clean this up a little bit, I get P is equal to XA PA star of T, and this is T bubble, if I want to be specific about it. This is also P bubble. Well, I guess it depends on which one you're given, right? If you're given pressure, you'd find the bubble point temperature. If you're given temperature, you'd find the bubble point pressure. So either one of them can be the bubble point given the other variable. And then I'm also going to substitute for XB 1 minus XA. So like I said, this one is also true. It's just that we're not using it as the constraint for finding the bubble point. PB star of T bubble, where once again, the vapor pressures would be found by Antoine's equation. So this is the equation that you would use to find the bubble point. In other words, if I was given what XA was and what P was, there would be one true value of temperature that would solve this equation. And I'll just write the formula for PB star. It's 10 to the power of A minus B over T plus C. So because T is in the exponent here on both vapor pressures, this can be a very challenging equation to solve algebraically if you wanted to solve for the bubble point temperature. I showed you how I would solve this using Microsoft Excel in a previous video. So this is the bubble point equation. All right, now let's talk about the dew point next. For the dew point, I'm going to use the other constraint. So my constraint for the bubble point was that the sum of the vapor phase mole fractions is equal to 1. For the dew point, I'm going to say the sum of the liquid phase mole fractions is equal to 1. And in my Raoult's laws, I'm just going to simply rearrange them to be equaling XA and XB. So XA is going to be equal to YA times P divided by the vapor pressure PA star of T, and XB is equal to YB times P divided by PB star of T. And I'll do the same thing for the dew point, that is add them together. And when I add them together, I get XA plus XB is equal to 1. All right, that was our main constraint, and that is equal to YA times P over PA star of T plus YB times P over PB star of T. I can do the same thing here where I clean it up just a little bit. There's really not much to clean up here. You could say 1 is equal to P over, it'd be 1 over PA star of T plus PB star. No, actually, it wouldn't be that. You have to cross multiply it. I'm just going to leave it like this. YA over PA star plus 1 minus YA over PB star of T. Okay, and this would be my dew point constraint. Once again, there's one true value of temperature for every corresponding pressure, or one value of pressure for every corresponding value of temperature for each mole fraction. So I have to have 2 out of those 3 variables set. This is the dew point constraint. All right, this is almost it for this video. On the next video, I'll tell you about a diagram that shows bubble points and dew points graphically. And these diagrams are called TXY, PXY diagrams, and they are much easier for solving these bubble point and dew point calculations, and also much easier for solving for what the compositions of your vapor and liquid phases would be at a given temperature and pressure that is at equilibrium. That'll be it for this video. Look out for that next video.